Okay, can you see my screen?
Yes, sir.
Okay. So in our last class, we have derived this equation, that is the induced EMF across the primary winding having n1 number of turns, and the mutual flux is phi, whose amplitude maximum value is phi m. Okay, and the equation is given by uh, please mute yourself. So the expression of induced EMF across the primary winding is given by equation 5, that is E1 equals to 4.44 F N1 phi m. Okay. Now the same flux is linking with the secondary winding also, because we are considering that the whole flux produced by the primary winding remains confined within the magnetic core. Therefore the total flux links with the secondary winding also. So we can apply the Faraday's law of electromagnetic induction in across the secondary winding also, because this winding is also linking with the same alternating flux or time varying flux. Therefore we can use the mathematical expression of Faraday's law of electromagnetic induction, that is E equals to minus of n d phi dt. So for secondary winding, the equation will be E2 equals to minus of n2 d phi dt. N2 is the number of turns in the secondary coil, and E2 is the induced EMF across the secondary winding. So across these two terminals we will get E2. Okay. So after putting the value of phi and differentiating with respect to t, we will get this expression E2 equals to minus of n2 omega phi m cos omega t, and if we express this cos omega t into sine, then we get this expression. So here EM2 is the maximum value of secondary induced EMF, which is equal to n2 omega phi m. So therefore we can find the RMS value of this induced EMF. So E2 equals to maximum value by root 2, so that is root 2 pi f into phi m, and that is also a similar expression like before, that is E1. So E2 equals to 4.44 f into phi m. So the only difference is the number of turns, the other terms remain same. Therefore from equations 5 and 7, equation 5 was E1 is equal to 4.44 f n1 phi m. We can write this, which is equal to n1 by n2. Now in other way we can express equation 5 and 7, that is E1 by N1 is equal to 4.44 F phi m, and that is also equal to E2 by N2. Okay, so we can write E1 by N1 is equal to E2 by N2 equals to 4.44 F phi m. Now what is this 4.44 F phi m? We call it the number of EMF per number of turns. Okay, EMF per turns. E1 is the total induced EMF across the primary having n1 number of turns, and E2 is the induced EMF across the secondary having n2 number of turns. From those two equations we can write E1 by N1, that is EMF, induced EMF in the primary per turn is equal to 4.44 F phi m, which is also same across the secondary winding, that is E2 by N2, that is EMF per turn in the secondary side is also same. So we can write EMF per turn in primary is equal to EMF per turn in secondary. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Anyone having any question up to this? related to this basic principle of transformer. No question. Okay. So here the basic principle is that while we are giving some voltage across any winding, it will produce some flux, and if that flux links with some other coil, there will be uh, some induced EMF across the second coil. If the flux produced by the primary is alternating or time varying in nature, okay, here both the windings are stationary, so there is no relative motion between them, that means between the source producing the magnetic flux and the coil. Okay, so this EMF is called static EMF. Here the flux is time varying, so that is why there will be some change in flux linkage, so we will get an EMF across the secondary winding. Okay, so that is the basic principle of transformer action, and we call it the transformer EMF. Okay, so now we will go to the second topic. This equivalent circuit is yet to be discussed. So we will go to the second topic, phasor diagrams on no load as well as full load. Now before going to the phasor diagram of a practical transformer, we have to consider the ideal two winding transformer. Okay, so what is an ideal transformer? Any transformer to be an ideal one, we have to assume certain conditions, and those conditions are like winding resistances are negligible. See, these two windings primary and secondary, they are made up of some conducting material, so there has to be some resistances, but for an ideal transformer we are considering that these windings do not have any resistances. Okay, second condition is all the flux set up by the primary links the secondary windings. That means all the flux is confined to the magnetic core, which means there is no leakage flux. Okay, no flux will leakage from the core of the transformer. Third condition is the core losses are negligible. That means we are assuming that there will be no eddy current loss, no hysteresis loss. And the fourth assumption is the core has constant permeability, which means the magnetization of the core is linear. Normally the magnetization, that is the BH curve of any ferromagnetic material, looks like this. Okay, for increasing current only. Okay, that means after a certain value of current or H equals to Ni by L, so we can consider H is proportional to I. So if I increases, H will increase. So this is the variation of B and H or phi I. Okay, so this is phi I curve or BH curve. Okay, so if we increase the current value, after a certain value of current, the flux value will not increase, that means it will saturate. Okay, but for ideal transformer we will consider that this core is having constant permeability, which means the magnetization curve is linear. That means we will consider up to this portion. Okay, before this, after this knee point we will not consider. Okay, so these are the four assumptions which are required for any transformer to be an ideal one. Okay, but any practical transformer, there will be some winding resistances, and there will be some leakage flux, and there will be some core losses, and the fourth assumption, that is the magnetic permeability of the core will have a constant value. That means its magnetization curve will be linear, and that is also not true, but in your syllabus we will always consider that the core has constant permeability, that means the magnetization curve will remain linear. Okay, we will consider the three assumptions, the first three assumptions, and we will incorporate the corrections for these assumptions only. Okay, later on we will discuss those corrections. Now how to draw the phasor diagram of an ideal transformer on no load condition. That means no load is connected across the secondary, that means this switch is open condition. Okay, so here the sinusoidal exciting current I is given by the equation Im equals to I max sin omega t. Though we are considering exciting current, but as we are considering ideal transformer, so there will be no core loss component of this exciting current. It will have only the magnetizing component. That is why we are writing IE as Im, which is the only magnetizing component in this case. So Im is I max sin omega t. Okay, so this is the sinusoidal exciting current. The flux produced by this current is given by phi equals to phi m sin omega t, and the two induced EMFs are given by these two equations, E1 N1 omega phi m sin omega t minus 90 degree and E2 equals to N2 omega phi m sin omega t minus 90 degree. Okay, now using these four equations we can draw the waveforms. See, first waveform is phi, this one, this dotted one actually. So this is phi, the variation of flux with respect to time. Then we can see from equation 1 that the exciting current I, which is having the magnetizing component only for the ideal transformer, Im, that is also in phase with phi. So this next curve Im is drawn here, which is shown by the symbol IE, that is the exciting current. Next, two induced EMFs E1 and E2, you can see from equations 3 and 4 that both these two EMFs are lagging the flux or the exciting current by an angle of 90 degree. So if we take the flux phasor as the reference phasor, we have to draw these E1 and E2 vertically downward direction. Okay, so using this waveform we can draw the phasor diagram. So first of all you have to consider phi as the reference phasor. Recall the convention of drawing any phasor diagram, that you have to consider the parameter or the quantity which is common to all as the reference phasor. So here which one is the common quantity? Hello?
Sir, phi m.
Phi. Okay, phi is the common parameter or quantity. So we take phi m as the reference phasor. Okay, and Im, that is in phase with phi m, so you can draw I along the same line and E1 and E2 vertically downward. Now as per Lenge's law, we know that the applied voltage V1 is equal to minus of E1. Okay, because this E1, the cause of the production of E1 is actually V1, that is the applied voltage, and so E1 is the effect, V1 is the cause, so effect will always oppose the cause. Okay, so that is why this V1 is taken equal but opposite in direction of E1 as per Lenge's law. Okay, so we can draw the phasor diagram using these notations, that phi is taken as the reference phasor which is drawn along the positive x direction, IE, that is the exciting current, is drawn along the same line because phi and IE both are in same phase. The two induced EMFs E1 and E2 are drawn vertically downward, that is making an angle of minus 90 degree with phi, because these two EMFs lag the flux phasor by an angle of 90 degree. Okay, and the applied voltage V1, which is opposite to that of E1, is drawn vertically upward direction along the positive y axis. Is it clear up to this?
Yes, sir.
Any question? Okay, as per the wave shape diagram, you can see the value of flux, that is the maximum value of flux is less than the maximum value of IE. Okay, but here in phasor diagram we have drawn phi greater than IE. Is it correct? Can we draw like this?
No, sir, we cannot draw it like this.
Why not?
Sir, because the phasor diagram, the length of the phasor is the maximum value.
No, we
So
can take
according,
RMS value also, no problem with that. No, actually we can draw like this, no problem. It depends on the scale factor. If you suppose the maximum value of flux is, suppose phi equals to 1.5 Weber, okay, and the maximum value of current is suppose 10 ampere. So you have to select one scale to find the length of the phasor. Okay, so suppose 1.5 Weber is equal to 3 centimeter. Okay, and that length shows this length. Okay, now if you select 5 ampere is equal to 1 centimeter, then this much length will show 10 ampere, isn't it?
yes, sir.
So we can draw like this, no problem. It depends, the length of the phasor depends on the scale factor, right? Okay, so why we draw like this, that is described here, which I have already discussed. So at t equals to 0, the flux phi is 0, it is drawn horizontally, same phase, current is in same phase, E1 E2 drawn downward because they lag the phi flux by an angle of 90 degree, and V1 opposite to E1, so that is vertically upward direction. Okay, now the same transformer under loaded condition, that means this switch is now closed. Okay, so if we close this switch, what will happen?
Current starts flowing through the secondary winding.
Yes, so let us take this current as I2. Okay, now actually the direction of this current will be in such a way that it will produce its own MMF N2I2, that is the secondary MMF F2, and this MMF will produce its own flux, suppose phi 2. Okay, and as per Lenz's law, the direction of this phi 2 will be in such a way that it will oppose the main flux phi. Is it clear?
Yes, sir.
The direction of, when we close the switch, this switch, a current will start flowing through this secondary winding, through load also, and this current will produce its own MMF F2, which is equal to N2I2, and this MMF will produce its own flux, and the direction of this flux will be opposite to that of main flux phi. So what will happen? It will try to reduce the value of flux phi, isn't it? This flux phi 2 will try to reduce the value of main flux phi, right?
Yes, sir.
Please repeat again.
When we close this switch S, a current will start flowing through the load as well as through the secondary winding, because a closed path will be there. This current, direction of current will be in such a way that it will produce its flux, which will be opposite in direction to that of main flux phi, this flux phi. This current I2 will produce its own MMF N2I2, that is F2, and this F2 will produce its own flux phi 2. This phi 2 will be in opposite direction to that of phi. Up to this, it is clear. This will happen as per Lenz's law.
Yes, sir. Clear,
Simply
sir.
the direction of phi, simply the direction of phi 2 will be opposite to that of main flux phi. Now, if they are in opposite direction, which means this phi 2 will try to reduce the value of phi. Okay. Now, if phi reduces, what will happen?
EMF induced reduces.
Yes, EMF E1 as well as E2 both will reduce. Okay, so let us consider the reduction of E1 only. What will happen if E1 reduces? So if phi reduces, E1 will reduce. Okay, now V1, that is equal to minus of E1 for an ideal transformer, because we have not considered the resistance of the winding as well as there is no leakage reactance, so there will be no other drop. V1 is directly equal to minus of E1. Okay, so if E1 reduces, it, which means V1 will reduce, isn't it?
Yes, sir.
But V1 cannot reduce. Why? Because this is the supply voltage. Whatever we are giving, that is fixed. V1 cannot reduce. That is fixed. Okay. This supply voltage, it cannot reduce. Okay. So which means E1 cannot reduce. So to have the same value of E1, this flux value must remain constant. What is the meaning of that? To remain the flux value constant, this current value I will increase. This I will increase because some portion will nullify the effect of this I2, that means phi 2. I2 is producing flux phi 2, which is trying to reduce the flux phi. So that effect has to be reduced by this current IE. Okay, so its value will increase. So some portion of IE will nullify the effect of I2, and the rest will produce the same amount of flux. In this way, this flux value phi remains constant. Is it clear?
Yes, sir.
So this flux value cannot reduce. Though there is some opposition, but that opposition has to be overcome by supplying more value of exciting current. Okay, so now we have two components of this current, primary current I1. One component is the exciting current IE, another component is the current which has to be opposite in direction to the load current, that means which is called the load component of primary current. We call it I1 dash. So now the primary current is not IE only, it is I1, which is having two components. One is IE, another is I1 dash. I1 dash is the component which is responsible for the which is nullifying the secondary current I2, the effect of secondary current I2. That means it is I1 dash is the load component of primary current, which is nullifying or which is opposing the reduction of flux phi. Okay, so it is the load component of primary current which is responsible for the flux to be remain constant. Is it clear?
Yes, sir.
Okay. So V1 cannot reduce, therefore E1 cannot reduce. Now to keep E1 constant, we must have a constant value of flux. For that, the primary winding draws more current. The excess current is I1 dash, that means the other component of primary current is I1 dash, to neutralize the demagnetizing effect of F2. Demagnetizing means the effect of reducing the flux phi. Phi is magnetic flux, which means it will magnetize the ferromagnetic core, and I2 is opposite. I2 is in such a direction that it will produce its own flux phi 2, which is in opposite direction to that of phi. That means it will try to magnetize the core in opposite direction. That is demagnetizing to the phi. Okay. Therefore, now we have two components of current, primary current. One is I1 dash, another is IE, and this I1 dash will produce its own MMF, that is I1 dash N1, which is equal to I2 N2, that is F2. Okay, so I1 dash N1 and I2 N2, these two components will nullify each other. Therefore, the rest of the current, that is the exciting current, will produce a fixed value of magnetic flux phi. Okay, which means, see, this value of ZL, load current ZL, load impedance ZL, this is a variable quantity because the load connected across the secondary can change any moment. Okay, so whenever there is a change in the load impedance value, the current value will also change. This I2 will also change depending on the value of load connected across the secondary. So as soon as there is a change in the secondary current, there will be some reflection of this change on the primary side. That means the value of I1 dash will also change at the same moment. Okay, so when this load across the secondary changes, load impedance value changes, I2 will change and its reflection will be a change in the I1 dash. So the total primary current will change. So that is why this statement, any change in the secondary current is at once reflected by a corresponding automatic change in the primary current, so that core flux remains unaltered. That means you cannot change the value of phi. This value remains fixed. Whatever happens in the secondary, there will be a reflection in the primary side. So that will, due to that change in secondary current, there will be only a change in the value of I1 dash only, no change in IE value, no change, this is fixed. But since I1 dash has changed, so the total primary current will change. Is it clear?
Yes, sir.
Okay. So here I1 dash is called the load component of primary current I1. So now the primary current is not IE only. After closing this switch, the primary current is not IE only, it is I1. Okay, and this I1 is equal to IE plus IE dash. Sorry,
It is I1 dash.
I1 dash. Okay, let me correct it. Oh, okay, mute yourself. So I1 is equal to IE plus I1 dash. Okay. So now we have to draw the phasor diagram of ideal transformer under loaded condition. So let us consider the secondary current I2 lags the secondary voltage V2. V2 is the voltage across the load terminals, and this V2 is equal to E2 because we have considered no winding resistance and no leakage flux, that means no leakage reactance also. So V2 equals to E2 for an ideal transformer. So let us consider that this I2 lags the secondary voltage V2 by an angle of theta 2, this angle. Okay. So from the phasor diagram of ideal transformer under no load condition, we already have this phasor phi, IE, E1, E2, and V1 equals to minus of E1. Okay. Now for loaded condition, we have to write E2 equals to V2, and then we have to draw V2, I2 lagging V2 by an angle of 90 degree. So this phasor, okay, and F2 is the MMF, secondary MMF, which is equal to N2I2. So F2 equals to N2I2, and this F2 is opposite to that of F1, which is primary MMF for load component only. So this is I1 dash N1. Since F1 and F2 are equal and they are in opposite direction, therefore I1 dash and F1 are drawn opposite to that of F2 and I2. So I2 is opposite to that of I1 dash, F2 is opposite to that of F1. Okay. So I1 dash and I2 are not equal, but they are equivalent. So how to calculate I1 dash from I2, that I will tell you later on. So here don't think that I1 dash is equal to I2. I1 dash is equivalent of I2, that is the reflection of I2 in the primary side. Okay. Now if we find the resultant of I1 dash and IE, then we will get the total primary current I1, and the angle between I1 and the applied voltage V1 is the primary phase angle, which is theta 1. Is it clear?
Yes, sir.
Yes, sir.
Anyone having any doubt? how to draw phasor diagram of an ideal transformer under loaded condition. First of all, you have to draw phi, taking it as the reference phasor. Then you have to draw I in phase with phi. Then you have to draw two EMFs lagging phi by an angle of 90 degree. Then you have to draw V1, which is equal but opposite in direction of E1. So V1 equals to minus of E1. So length of E1 and V1 will be equal. Okay. So this is up to this is the phasor diagram for ideal transformer under no load condition. Then you have to draw the other phasors for loaded condition. So first of all, you have to draw I2, that is the load current. First of all, you have to write E2 equals to V2. Then you have to draw I2 lagging V2 or I2 by an angle of theta 2. Then you have to draw F2. Then opposite to I2, you have to draw I1 dash, which is not equal to I2. Then you have to draw F2 equal to F1. Okay. Now find the resultant of I1 dash and IE. You will get I1, and the angle between I1 and V1 is theta 1. Okay. So we can write this equation now. I1 is equal to I1 dash plus IE. Now some simplification. Yes. Yes, please.
Sir, that F1 and F2, can you explain that again? That is electromotive force due to I2 and I1 dash or I1?
No. Not electromotive force, magnetomotive force, MMF.
Sir, I2 and
Yes,
I1
you
dash.
can. Yes, F2 is MMF produced by current I2, which is equal to I2 into N2. Okay, and F1 is opposite to that of F2 and equal in magnitude, because it has to be equal, otherwise it cannot nullify F2 fully. Okay, and that F1 is equal to I1 dash, which is the load component of primary current, into number of turns in the primary, that is I1 dash N1.
Yes, sir.
It is not I1 into N1. Please observe this equation very carefully. F1 is not equal to I1 N1. It is I1 dash N1. Okay. Now for simplification, we can take this exciting current value is very small with respect to load current. For a practical transformer, normally the value of exciting current is about 2 to 6% of full load current. 2 to 6% of I1, that is rated current of primary side, which means suppose the primary current is 100 ampere, so the exciting current will be 2 ampere to 6 ampere. Okay, so in comparison to this 100 ampere, this 2 to 6 ampere is very low, so we can neglect this exciting current. Okay, for simplification, now consider the equation I1 is equal to IE plus I1 dash. So if we neglect this IE equal to 0, what is it? What we are getting? I1 equals to I1 dash, isn't it?
Yes, sir.
In that case, we can write F1 is equal to I1 N1, which is equal to F2. So we can write I1 N1 equals to I2 N2. Most of the part of I1 is the load component. Okay, so that is why this F2, which is I2 N2, can be taken approximately equal to the primary current I1 N1. Though I1 is greater than I2, okay, but the difference is only due to exciting current, which is having a very low value with respect to the rated current I1. Therefore, we can take this equation. We can write this equation. Any confusion?
No, sir.
No, sir.
Okay. So primary ampere turns equal to secondary ampere turns. This I into N, that means current into number of turns, that is called ampere turns. So I1 N1 is equal to I2 N2, means primary ampere turns equal to secondary ampere turns. You know the unit of MMF is ampere turns, isn't it?
Yes, sir.
Okay. So therefore, for an ideal transformer with exciting current is equal to 0, we can write V1 by V2 is equal to E1 by E2 is equal to N1 by N2 is equal to I2 by I1. This relation is very, very important. From the transformer EMF equation, we have got this part. Then from phasor diagram, we have seen that V1 is equal to E1 and V2 is equal to E2 for an ideal transformer though. And from this equation, we have seen that I1 N1 equals to I2 N2, which means N1 by N2 is equal to I2 by I1. Okay. So from these two equations and from the induced EMF equation, we can write up to this, and from this equation we can write this. Is it clear?
Yes, sir.
So
Yes,
remember
sir.
this equation. Remember this equation, V1 by V2 is equal to E1 by E2 is equal to N1 by N2 is equal to I2 by I1, not I1 by I2. Okay. And also we can write E1 I1. See, E1 into I1 is equal to E2 by E2 into I2, and we can also write V1 I1 is equal to V2 I2. Now, what is this V1 I1 and V2 I2? Product of voltage and current. What is it?
Power.
Yes, volt ampere. Volt ampere. So, which means the power remains same. Whatever power we are supplying from the primary side, we are getting equal amount of power across the secondary side. There is no loss. Why there is no loss? Because we are considering ideal transformer, and we have, for an ideal transformer, we have neglected the core losses and we have considered there is no winding resistance. Since there is no winding resistance, so no question of copper loss or ohmic loss, that means I square R loss. Okay, no resistance, no I square R, isn't it? So that is why for an ideal transformer, the volt ampere or the power remains same. Is it clear?
Yes, sir.
Okay. Now, impedance transformation. What is the meaning of this? See, here we have considered one schematic diagram of an ideal transformer having N1 number of turns in the primary, and V1 is the applied voltage, I1 is primary current, and across the secondary there are N2 number of turns and one load impedance Z2 is connected, and for that current in the secondary side is I2. Okay. Now, for the secondary circuit, we can write V2 by I2 equals to Z2, simply Ohm's law. Z2 is the load impedance or any impedance connected across the secondary terminal. So Z2 equals to V2 by I2. That means due to the presence of this Z2, this I2 current is flowing. We can say that. Okay. Now for an ideal transformer, from equation 8 we can write this equation: V1 by N1 is equal to V2 by N2. Recall equation 8, E1 by E2 is equal to V2 by V1 by V2 is equal to N1 by N2 is equal to I2 by I1. So from that equation we can write this: V1 by N1 equals to V2 by N2, and I1 N1, it was N1 by N2 is equal to I2 by I1. So we can write I1 N1 equals to I2 N2. So from these two equations we can write these two equations. From this equation we can write V1 is equal to this, and from this equation we can write I1 equals to this. Okay. Now divide equation 11 by 12. That means we want to calculate V1 by I1. So what is it? We are getting V1 by I1 is equal to this, which is equal to N1 by N2 whole square into V2 by I2. Now what is V2 by I2?
Z2.
Z2.
And N1 by N2, this is called the turns ratio. So turns ratio squared into Z2. So we can write N1 by N2 whole square into Z2, which is equal to Z2 dashed. See, Z2, this is the impedance value and you are multiplying it by some constant, which means the effect remains same. It as a whole we can say it is some impedance, isn't it? If you multiply 2 ohm by 4, you obviously will get 8 ohm, isn't it?
Yes, sir.
Yes, sir.
So Z2 into N1 by N2 dash square is some other impedance having value Z2 dashed.
Yes, sir.
Okay. So Z2 dashed is equal to V1 by I1. What is the meaning of this? That means we can connect this Z2 dashed in the primary side and the current relation, that is V1 by I1, will remain same. Previously this Z2 was connected across the secondary. Now we have calculated some value of impedance which is equal to Z2 dashed. Now if we connect this Z2 dashed in the primary side, this voltage ratio and current ratio all remain same. That means the effect of Z2 remains same. Though we have replaced this Z2 by some other value of impedance and connected it to the primary. The current value, that means the transfer of current from primary to secondary, transfer of voltage from primary to secondary, that all remains same. Got my point?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
So
Yes,
now we can draw a new schematic diagram having no impedance in the secondary side. So V2, that means the voltage across that load impedance or the Z2 is equals to 0 now. And we have connected the equivalent impedance of Z2, which is equal to Z2 dash, and Z2 dash, sorry, N1 by N2 whole square. So this is the equivalent of Z2 while connected in the primary side. So this impedance is now connected in the primary side. Okay, so keeping all these transformation of voltage and current same, we have replaced the impedance Z2 by Z2 dashed and connecting it to the primary side. So that is called referring any impedance from one side to other. Here we have transferred one impedance from secondary to primary. Okay, so Z2 dashed is the impedance which has been referred from secondary to primary. So this is the simplified diagram having the primary side only, no requirement of secondary side because no impedance is there, so no voltage across that. So we can draw this figure also. Okay, and same way we can refer any impedance from primary to secondary. So here Z1 dash will be Z1 into N2 by N1 whole square. Why N2 by N1? Because we are referring the impedance to secondary. So while you are going to refer or transfer any impedance from one side to other, you have to take the turns ratio in such a way that the number of turns of that side to which you are referring, that you have to keep on in the denominator. Okay, while you are transferring in the primary side, in that case turns ratio will be N1 by N2 whole square. While you are transferring to secondary side, then N2 by N1. In this way you have to remember. Okay, so transferring an impedance from one side of a transformer to the other side is called referring the impedance to the other side. So here you are referring something from one side to other. Is it clear how to refer some impedance from one side to other?
Yes, sir.
Yes, sir.
Okay, let us summarize what we have learnt till now. Voltages are transferred in the direct ratio, that means from one side to other. If we transfer or refer any voltage, then we have to use the direct ratio, that is V1 by V2 equals to N1 by N2. Okay, that means V1 is equal to V2 into N1 by N2, which means V2, we are transferring V2 to the primary side. Okay, next, currents in the reverse ratio, as we have seen, I2 by I1 equals to N1 by N2. See, I2 by I1 ratio is N1 by N2, so reverse ratio or inverse ratio. Impedances in the direct ratio squared, as we have discussed just now. So Z2 dash equals to N1 by N2 whole square Z2. And what about the power? Volt ampere remains unchanged, that is V1 I1 equals to V2 I2. Is it clear?
Yes, sir.
Yes, sir.
Okay, time is over today. Up to this, don't leave, I have to take attendance.